Afternoon, ladies and gentlemen. Thank you for coming to the final current monthly presentation of 2024. Dr. Fran Lee, our leader and director, is traveling today, so he is not here to introduce our scholar today who is presenting. That person is Dr. Kai Sun. He received his PhD from Tsinghua University in Beijing back in 2004. After that, he worked for EPRI in Palo Alto, California, prior to coming to the University of Tennessee in 2012. From 2019 to 2020, he was a visiting scholar at Harvard before returning back to us at UT. And today he will be talking to us about power grids. So, Dr. Sun, thank you for agreeing to present to us, and please take it away, sir.
Okay. Thank you, Michael, for the introduction. Yeah, from the list of participants, I see a lot of familiar names and old friends. So hopefully we can have very interesting discussion at the end of the presentation. So let's move to the topic of this presentation. I select this topic because this has been my personal research interest for almost like 20 years. I would say at least 20 years. So today I'm going to integrate some very interesting work and result in past 10 to 20 years, and hopefully I can give you a big picture about what is the state of the art of the research and available tools for cascading failures, and what the challenges that we are facing, and what can we do to make a change. So I'll focus on the simulation analysis and control of cascading failures. Somebody use cascading outages or cascading failure with a similar term. So my most of material can be applied to both. Okay, so I'm going to cover some background information about historical blackouts, cascading events, the risks, and the challenges. Then I will focus on some highlights of the research by my team in past, I would say, 12 years since I joined the University of Tennessee. I will be focusing on the efficient simulation tools by considering multi-time scale dynamics of the cascading failures. And also I will introduce some ideas to use the data-driven tools to study the cascading failure modes and mitigation actions. And also I will show some comparison result for different strategies of mitigation and prevention. Finally, I will give some conclusions, also some suggestions for the next step. Okay, before I start my technical presentation, I want to just highly recommend everyone to buy or to find those two books. The right book published by Springer was this year, and this is this book is edited by me, but I also contribute 3 chapters. Today, some important research highlights will be covered by this book. It also includes some other very important research results. For example, from Professor Ian Dobson with Iowa State University, and from Dr. Milorad Pavic from used to be with Idaho Power, and he also contributed a chapter about the status of the industry. And there are also other very interesting work related to cascading failure, risk assessment, modeling, and simulation. And the yellow book was published like 6 years ago. So this one include my PhD dissertation work, and also some of my work at EPRI, which covered how to do the control, including the system islanding, system restoration, black star, to mitigate or prevent cascading failures. So please find those books if you're interested in this topic. Very, very likely those two are only existing power system books on cascading failures. So if you try to search the keywords cascading failures in any book title for power grid, those two could be the only 2 books you can find. Okay, this slide just gave you some overview about the past famous historical blackout event. So I started from 1965 northeastern blackout event. So this is very important event. I think after this event, we had EPRI, Electric Power Research Institute, and we changed the way to study and for the research and for the planning and for the operation of the power grid. We start realize we have to study the power grid itself as a whole, not just as individual component, in order to prevent some really bad event like cascading blackouts. So in this table, it just shows some information about the duration of each cascading failure event or blackout, and also how many people are influenced. And so if we show those data on this the chart on the right-hand side, and we somehow like just indicate there's some try to do like a linear fitting, but it's hard, right? It can be because it covers many different countries in the world. But basically, you can tell. So when the duration of the blackout or the restoration increase, and more people will be affected. So definitely want to prevent large-scale blackouts, and if they really happen, we want to bring the system back as soon as possible. So this slide just gave you a summary of some common factors and the lessons learned from the historical blackout. The first is about the common factors. I guess many of you already know those three common factors, which are the three T's, the so-called three T's, which indicate most of the historical blackouts are caused by inadequate tools, inadequate trainings, and inadequate tree management. So if you have a better tools to simulate, analyze cascading failures, or you can provide more trainings for system operator to take actions timely if cascading really happen, or you can just trim the trees more often, right, to mitigate the chance to have short circuit. So you're going to lower the risk for cascading blackouts. There are some specific technical areas for improvement, which is summarized in the book, the red book I show in the third slide. So there are something we can learn from those historical blackouts, such as we need to ensure timely maintenance and update of the transmission infrastructure. If any line has a reduced room for power flows, and if something happens, those lines will be congested and a violation may happen. That can trigger some contingencies. We need to improve the measurements and communication system with cybersecurity, because in the table, there's one cascading blackout event was really caused by the cyber attack, which is in Ukraine. Definitely, that may not apply to the US power grid or like Canadian power grid, but the cybersecurity is a potential threat to trigger cascading failures. The next one is we need to strengthen the grid monitoring and situation awareness. We need to have the real-time tools to indicate the status of the system. And if there's any potential risk for cascading failures or major event, we really need to be aware of that and take some proactive action. The next one is to just enhance contingency analysis. We need to really address the potential system vulnerability by the analysis. So we also need to design the effective emergency control remediation or protection scheme, especially for wide area control strategy, because if cascading failure happens, it's not just single event or two events. It can just spread out, propagate to a wider area. You really need to be prepared at the system level, not at just local equipment level. The next, we need to provide adequate training to operators and manage major power outage and system restoration. So also, there will be some other concerns about information sharing, coordination among different operators. So especially in the US, in some area, the power grid may be operated by different utility companies, and also there could be may have to involve multiple system operator, like some major blackout event in northeastern region, which can involve ISO New England, New York ISO, and PJM. They can involve multiple, even MISO, multiple operators of the system. Okay, so next, let's talk about the how to estimate the risk of black holes. So a commonly accepted formula to estimate the risk of a black holes or the cascading events will be this one. So the risk can be defined as a product of the cost of the black hole and the probability of the black hole. Okay, so we need to know both the cost and probability. So if we use the black hole size in terms of either the number of the line outages or amount of load shedding, so anyway, so if you want to use that size as the cost for the black hole, and you do need to know the probability to have the black hole in such size. So we need to study the probability distribution of black hole size. Sorry, here it should be black hole. So there's three potential probability distribution depending on how strong your system is. So if you're operating a very strong system, which means either each line can have very large margin of security, reliability, or the load is very low. Okay, so each line will have room to deliver more power. So if that's the case, the probability distribution will be very likely exponential tail, which means for the failures with low cost black hole, that probability will be much higher than the failures involving multiple bigger size of black hole. So the risk for large black hole will be very low. So the engineer need to focus on the for the small size of black hole to prevent. But when the load increase to some marginal level, so for instance, near some critical threshold, and the distribution will become approximate power law shape, which means so the risk for black hole size, small size, or large size will have similar risk. So the engineer need to study both the small black hole and also the large black hole. But if the system is heavily loaded with a very high loading condition, and high risk will be the case for large black holes. So you need to prevent large black hole because that can more likely to happen, and also if it happens, it give you the huge cost. And so that largely increase the risk. So if you try to visualize those three probability distributions, so here is a figure generated by my student. So the X is the number of line outages, which is basically the cost of black hole size, and Y is the probability. So the product of the number will just tell you the total risk. And here the figure is shown using the logarithmic, which means you can tell it's not linearly scaled. But so for if the black hole distribution follow a power law, so that will be a straight line. So now the orange line is fitted by using the data when the load reaches the critical level. So you see the risk on both small black hole and large black hole will have similar risk. But if the load is much lower than the critical level, so only the small black hole will have very high probability. So you need to focus on those small black hole. When the load is too heavy, and that can make some large black hole to be more likely to happen. So that largely increase the risk. All right, so now let's just compare what we learned from the previous slide to today's industry practices on contingency analysis. Because when you try to study potential cascading failure, you have to simulate or analyze some contingencies, and you definitely cannot study any possible contingencies. Just think about if you have a power grid with thousands or tens of thousands transmission line component, you cannot just study any combinations of contingencies. You have to categorize some contingencies and only focus on the ones with high likelihood or high probability. Okay, so if we categorize potential contingencies by those colors, like for example, there could be a single generator outage using this green dot, and they have a single line outage using this blue dot, and you can have a double line, maybe just a double -1, -1, -2 outage, or you can have a extreme event which involve more outages of lines or generators. So if you try to visualize those contingencies along this chart about cause versus the probability, which is consequences versus the likelihood, and they will be distributed along this curve. Okay, so we know if the load is the critical, so this line is more like a power law curve, and if it's the load is lower, it will be pretty much focused on the low cost end, right? And if the load is high, it will be moved to the right hand side. But basically, it will just stay along this curve. Okay. So if we compare those contingencies to the existing category defined by NERC, so NERC right now define P0, P1 to P2, and P3 to P7. So basically, P0 means just a normal system. There's no contingencies at all, right? It's -0. And P1 to P2 basically just means -1, which means you just lost a single component. So it's just a normal system losing a single element. It can be generator, line, transformer, or maybe some bus section or shunt. Okay, that's P1 to P2. And starting from P3, you need to consider more than one contingency. It can be just N-2 or N-K. So K here can be more than 3. Okay, so if you try to visualize those categories on the left-hand side chart, okay, it will be roughly like this one. So P1 to P2 will cover some low cost but high likelihood, high probability events. And P3 to P7 will cover either low or high cost, but the probability can be lower, much lower than the P1 to P2. And so the P1 to P7 pretty much from the table is defined by NERC, which are the contingencies utility companies, they have to study. There's no excuse. But they are not enough to cover all potential cascading failure mode, because there's some extreme event, they will involve more than 3 or many components. So there can be those red dots, but they cannot be covered by P3 to P7. So currently the power company just select some of the MSK or extreme event to study. So if those events happened in the past, or they just happen start from the same local area, they can study those contingencies. The examples such as just loss of more than 2 generator circuit transformer in the same area, loss of most of all elements, no matter how many elements there are in the same local area connected to the same substation. There's some wide area, but they have the same root cause, such as there's some power plant, they're affected by the same pipeline, or there's some water, nuclear, welfare, or severe weather condition. For instance, there's maybe tornado moving in the same direction, so it will impact multiple lines and transformers. So utility company definitely need to cover those Mexican contingencies. But they are not enough to cover all potential extreme events. Some extreme events may increase the likelihood when the system is stressed. So we need to have some tools to do the pre-screening to identify those high likelihood events and to do the study, even if we're not able to cover all potential events. Okay, so what is the state of the art for simulation, analysis, and control of cascading failures? So regarding modeling, for analysis or simulation purpose, there are 2 types of model. The first type is a probabilistic model. The examples such as a cascade model, branching process model, indirectional influence graph model, and those models they're high-level models. So they may not have the details of the power system or even the topology. They just purely for estimating the probability of cascading failure modes. Okay, So their purpose is only just to do the study, just give you estimation of potential risk of one type of cascading failures. The second type model is a physical model. Their purpose is just to do the simulation study. So you can build like a fully dynamic model, just include everything, all the generator lines or protections and everything, every dynamic device can be modeled in your detailed model. Then you can just run the full time domain simulation. Or you can consider the multi-time scale dynamics of the system and you only focus on the modeling on some selected scale of dynamics. Or you can only focus on like a steady state or quasi-steady state behaviors of the grid. But there will be a trade-off between the accuracy of simulation and the speed of simulation. So if you use a very detailed dynamic model, it can be extremely slow because if you think about any realistic cascading event from the first line trip or first contingency until the system collapse, that can last maybe several hours or maybe tens of hours. If you really just try to capture the change, the initial change from the normal condition. So that can last a very long time. If you perform a fully dynamic simulation to cover this entire process, that's really challenging. So you have to select your simulation and the computation on very important dynamics that can cause that can tell how the failure will propagate. Regarding prevention, so now the major method is just to do the condition analysis, right? Using the categories defined by NERC, like from P1 to P7. So the condition analysis can be a fully dynamic simulation to do the transient stability assessment, or it can be just purely a steady state, only just run power flow to check voltage security or voltage stability. So currently, there are not enough methods to help engineers or to rank MSK contingencies because the cascading failures will be among those MSK scenarios. But if you don't scan or study all possible MSK scenarios, you may miss some potential cascading failure modes. So it will be important to understand the interdependence or interactions or causality among failures. Because some failures, they can be when you have concurrent failures coming on the grid, you really need to understand the mechanism to cause one failure trigger the other failure. So if you have such information, that can largely help you to narrow down the small size of failure to study for MSK. For mitigation, so today's strategies for mitigating large-scale power outage are mainly just automatic special protection system, SPS, or remedial action schemes, RAS, such as do load shedding, network reconfiguration, or even controlled islanding. But those control actions are basically scenario-based. So the engineer need to conduct enough study and for such scenario and design automatic system to react to the happening of the event and trigger some protective or the contractions. So they are not adaptive enough. And most of the special protection system or remedial action scheme don't use wide area data sufficiently. I know some of them may involve the data from remote area by using like a single phaser type of technology, but basically those methods are still based on using the conventional the measurement setup. For restoration, so if a cascading failure really happen, the operator need to go through a very time-consuming black star procedure. So the lack of the operator decision support or real-time navigation is still some concern. Like the projects have been involved in April is just to develop the decision support for the operators, so it can help them to visualize potential paths to bring the system back faster. But that is not the focus of this presentation. This slide summarize some existing models or tools to model simulate cascading failures. So it covers both physical models and also the probabilistic model. So you can see there's some like OPA model, which has been used by a lot of researchers to understand the mechanism of failure propagation. So I also introduced some of the work related to OPA model, and there are also some other high-level models. There's some like tools which can simulate or study. For instance, this is a transcare was developed by April, which can simulate the protection logic of the cascading failures. There's also some interaction model that's developed by my team. I will also cover that type of model. So if you want to find more detailed information, you can find this paper, this review paper, so which give you more comparison and more information about those models. I have to add the following remark. The first one is one sentence I learned back to maybe 2007 or 2008 when John April during the advisory meeting, and there's one engineer from a utility company, and he complained that my best planning engineers spend 80% of their time validating component models. Okay, so which means, so I put this sentence here, just want to emphasize. So even you have a good model. So in this table, there's many different options for model. Even you pick the right model for your system, you still need to validate this model, which means you need to make sure the configurations, the parameters, or setup of the model really match the behavior of your system. So selecting the model is not completing your job to do the simulation. You still need to make sure the model, all the parameter details are accurate enough. So the planning engineer, they face such challenge, even if they have the right model, okay? But in order to get all the parameter accurate, they need to spend a lot of time, try to validate, try to adjust the parameter and compare their simulation result to the real measurements and try to adjust those parameters. That's very challenging work. And most validated component model are only insured for MS1, MS2 conditions, okay? So they are not validated for cascading failures. So I have to emphasize this one, all right? So think about if you work with some power companies to develop the simulation tools for cascading failure, you definitely can get the model like PSSC model, the dynamic model, protection model, everything, okay? But, and also each component in the model can be validated, okay? Using, for example, using the digital fault recorder, they can capture the real event. They match the simulation versus the real measurement. But that validation is only ensured for just typical contingencies. So by typical, I mean MS1, MS2, or some contingencies you can observe they have more likelihood to happen. But cascading failure is really a different story. Okay, they really put the system to the extreme condition. So those models may not be guaranteed to accurately show what your system is going to behave under extreme event. Okay, so which means all models face validation challenges. Okay, so then there'll be, just think about this one. So it doesn't mean the more detailed model will be necessarily better, right? Because more detailed model means more parameter to be validated. So if you can simplify your model somehow and only keep the key dynamics for modeling and for simulation, that may give you a not very bad result. It can give you very much even better result. So now I have to emphasize the multi-timescale dynamics with cascading process. So if we use 2003 blackout as one example, if we try to visualize what's happening from the first event when the system is in normal until the system collapses, that then can take a number of stages, okay? So the first event may happen at a certain clock, and the system collapse may happen after the 16 clock. That lasts about 3 hours. And even after the 16 o'clock, the 4 p.m., and the system will have more failures and will be involved in the fast dynamic process until blackout really happens. So that can involve a long process. So if we really want to model the whole process accurately, we do need to consider all the following dynamics. The first one is a slow change in the steady state operating condition, because in such like 3 hours or 4 hours, the load can change, or generation can be redispatched. Even the network may have some change or switching. So that such dynamic is slow, but they can take hours to happen. But you need to consider such behaviors. Some faster dynamic could be like quasi steady state. By quasi steady state, which means they are really dynamic behavior, but we don't have to consider the detailed dynamic. We can somehow simplify dynamic using like algebra equation. We don't have to introduce differential equation to model such dynamics. So we call it a quasi steady state behavior. Examples such as the change in the load and generation. So such time scale could be in minutes. And if something happens, there will be a transient dynamic, and the generator may lose stability. So you do need to consider the transient stability of generators and even oscillation of generator. So such dynamic will be in the time scale of electromechanical dynamics, usually in seconds. Okay, protective switches may happen in milliseconds, and if there's some electromagnetic transient dynamic, that could be even faster. In the future, the grid can integrate a lot of inverter-based renewable energy resources, IBRs, right? So those control can be in the electromagnetic transient dynamic scale. So which means if I have such system, you want to cover all potential dynamic. Any dynamic can be some trigger of the failure to propagate in the next stage to cause cascading effect. So if you want to cover all the dynamics, that's very challenging, okay? Because the grid model will be highly steep. So if you compare the largest time scale or the smallest time scale, so the difference can be 10 to the power 9, right? That's a highly steep system. It's extremely time consuming to simulate. For instance, if you want to simulate the cascading process for 1 hour, a couple hours, and if I really want to cover some electromagnetic transient dynamic, I will use like a millisecond or microsecond and time scale. So that will take maybe 10 to the 10 time step to finish the simulation. Is extremely slow. Okay, so now this one just gave the big picture on what my team have done in the past 10 years. We really want to build up some decision support system against cascading failures, and we focus on 2 areas. The first area is modeling and simulation. So we want to provide a number of models that's different level of details for selection. And also we want to give multiple options from very detailed simulation to very high level simulation, depend on where you want to apply those tools, either in the planning stage or operation stage. And also we develop another set of methods for analysis and control to design a mitigation strategy against cascading failures. So such analysis and control strategy can be developed based on the data set of cascade, which are cascading events. They can be from historical event or from a simulated cascading events. Okay. Let's first quickly talk about the modeling and simulation. So if we want to differentiate those models based on their speed or the accuracy for simulation, so the bottom one will be the fastest model, and the top one will be most accurate model. So most accurate model will be the fully dynamic model. But as I said, if you choose to use fully dynamic model for cascading failure simulation, you have to face 2 challenges. The first one is not every single model is fully validated for extreme condition. Okay. Second, the simulation can be extremely slow because the model will be highly steep model. Definitely, you can just consider multi-time scales and only focus on the some time scale. Like you consider maybe the early stage, some failure will caused by weather condition. There will be some by the load, by the response of the system, And so you can choose some critical dynamics to model. And for the bottom model, fuzzy model will be the so-called the OPA model, and which use the DC power flow model and to consider to only run DC power flow and to check a line limit and to determine load shedding, and also to emulate how the operator will dispatch the system. So this is the fuzzy model. It's purely based on static condition and using the DC power flow. So the fully dynamic models and the DCOPA model are what we already available, okay, in the literature. And if you want to upgrade the DCOPA model, so the next one will be ACOPA model, so it will replace the DC power flow by AC power flow. So then you're able to simulate the voltage collapse and under voltage load shedding. And so next you can add the frequency regulation to the power flow models, and you'll also be able to simulate under frequency load shedding. Okay, and you can also add some transient stability simulation to interact with the OPM model, and then you'll be able to cover dynamics. And you can also skip over some very slow dynamic and focus the transient stability simulation only on a short period after each switch. If you want to even try to minimize the time domain simulation, you can just apply the NA function to help you to predict the stability. That can make the simulation even faster. Okay, so those are the list of models, and we can provide based on the research of my team. So in the next block, there's a number of technologies we can utilize to do the analysis and control. The first one is learning-based models. It can be like JN-based model, the Markov train-based model, or even the reinforcement learning. So today I'm going to just highlight some of the results. The next one is very important, which is a data-driven model, based on either historical event or simulated cascading failures. So this model tries to identify or quantify the interdependence of failures and rank the failures and try to predict or estimate the causality of failures. And you can organize such a model and visualize by like a multi-layer intention graph, and which can tell you the mechanism of failure propagation in the early stage and in the middle stage and late stage. So you can also design a strategy to update such a model and graph dynamically based on the system condition for online use. And you can also improve the model to give you more accurate probabilities, and such as you can be more prepared for cascading failures. This slide just highlight one study done by my group and try to utilize the multi-time scale model and try to simulate the 2003 blackout. So this figure does show the full stage of a 2003 blackout. And if you run full time domain simulation, it's very challenging. But you can definitely just identify the key dynamics of behavioral grid, which can really cause the outage propagation. So we can categorize such events into 3 different time scale, from the short time scale, mid time scale to long time scale, and focus the modeling only on each individual action. So this just gives you an example and what model you need to simulate. For example, the load variation is part of this long-term process, and there could be some heat accumulation process, which can influence some midterm dynamics. If there's a like power flow or transient dynamic, continuous immersive control, that fall into the short-term process. By interacting multiple simulators, some run at very fast time scale, at very small time step, or some run at a much bigger time step. So by integrating those 3 simulators, you can efficiently simulate cascading failure. So this figure does show the cascading process we simulated. You can tell it's very similar to the 2003 blackout using the Eastern connection model. Okay, so next few model will be based on the OPA model. OPA model was originally developed by Oak Ridge, Peace Circle, and Alaska, and that's why the model is called OPA. So this one, the focus of this model to understand the self-organization process of the system. So from a long-term point of view, so it's not really for simulating cascading failure, but it can be improved to provide a simulator for cascading failures. So the model considers two types of dynamics in two time scale. The first one is called the fast time scale, but fast time scale is not that the fast dynamic we talk about in power system. It really means like cascade of failure control. So the time scale is in days, right? So each day there could be the cascade of events which can be started and finished in the same day. So each day there will be a cascading event. So you can simulate many days to create a data set of event. Okay. If your system has a lot of cascade, you're going to upgrade system. So this flow chart just indicates the basic idea how to utilize the fast dynamic module of the OPA model to create a data set of cascading failure. For instance, you can set up some initial line outage, and if the line outage, they can take remedial actions. You can run the optimal power flow. So it can be based on DC power flow or AC power flow, depending on how accurate you want to capture the failure. So if there's a overloading, you're going to trip the line and check the other lines that continue this process. Another component with the OPA model would be the slow dynamic module. So that really consider the time frame of years. So it will simulate maybe thousands of days. Each time if there's a failure happens, you can consider upgrade the transmission line, increase the capacity. So gradually your system will become stabilized in terms of the capacity of the system, and you can with the load growth. So we can use this module to create the line limit or test bed for cascading failure simulation. This original OPA model, usually we just call it a DC OPA, just try to differentiate from other improved model, because this one is based on DC power flow. So you can only just simulate line outage, overloading, and generator trip due to a line landing. Okay, so next model is AC OPA. So that replaces the DC power flow by AC power flow, so such that you can simulate the voltage collapse and the voltage load shedding as well. Those two are actually the work already in the literature. So this slide just show one study my student did try to utilize DC OPA module for the slow dynamic component to create a test bed for cascading failure simulation. So we studied one NBCC test bed with 140 buses and 40 generators, and we simulated the same system for more than 3,000 days, right? They take a lot of years, and with random initial failures, and we let the load grow at a very slow speed. And if any line is overloaded, we'll just increase the limit by a very small percentage. And finally, after long process, after 60,000 days, so we will see a pretty even exponential growth of the line limit and the load, and we can normalize the line limit back to the base case load, and we'll see a stable line limit. Okay, so this is like growing line limit, but when you normalize back to the base case condition, each line will have stable limit. Okay, so it's not highly dependent on how you start this simulation. So when you run such simulation upgrading process for long enough time, finally you will have a very stable line limit. We can use those limits for the cascading failure simulation. So this figure just visualize how the when we generate this test bed and we run some cascading failure simulation, and those arrows, right arrow just indicate how one failure can cause the next failure. This is one way to visualize the interactions of failures, which is called interaction model, interaction graph. So the green lines are the components, which are important components, which can cause other failures. So if you only visualize the key component and the linkage of those key components, you can know there's about 15 key components, okay? So they cause almost like 70% of failures of other components. So if you can identify those key components and try to do some mitigation, you can save the system for a lot of chances. And there are also like 25 key links, which means one key component failure can cause another failures. Those links, if you only just consider less than 1% of all potential links, they only just have 25 such key links. They cover, they have the total weight of almost like 40% of all potential links. So this one just give you ideas. If you identify the key component link, you can actually understand where the cascading failure can start and how it can propagate to the rest of your system. These slides give you one idea to still use ACOPA model, which is steady state model, but we add frequency regulation into the model. So we don't run any time domain simulation. We want to make sure the quasi steady state behavior of the grid and the cascading failure can cover like line trips, voltage collapse, and the voltage load shedding, frequency instability, and then the frequency load shedding without running time domain simulation. Okay. So the idea is just to add the frequency dependent load model and the governor model into the power flow equation. So you're going to extend the power flow equation to add the frequency division to solve this frequency dependent power flow problem. And you can design the generator trip strategies based on the frequency division. So if the frequency is too high, there will be too high, there will be over frequency protection. If it's too low, it will be under frequency protection. So you can design such strategy based on NERSC standard or some industry practice. Then you can do the simulation. So this is improved OPA model by adding the frequency function into this model. So you can integrate the under frequency load shedding and generator frequency protection. So for instance, you can compare frequency to the different threshold and decide which generator to be tripped. Then running this simulation, you don't have to consider dynamic model, but you still can capture the frequency dependent event and their cascading failures. So if you compare the result of this model to the dynamic simulation and also ACOPA model without frequency, the first comparison will be with the fully dynamic model. So for fully dynamic model, this is a simple scenario by line switching to cause islanding of the MPCC system. So it starts from 60 Hertz after islanding. One island will be operated at frequency higher than 60, the other will be lower than 60. Okay, and this is from time domain simulation. This is from the this frequency embedded OPA model, ACOPA-FF. So by only running the power flow, integrating the frequency model, you can have the same frequency calculated from power flow. This is a comparison between the ACOPA model and this frequency-dependent OPA model. And for the frequency-dependent OPA model, because it can also simulate any frequency load shedding, so it's going to tell there's a more load loss due to the cascading failures. But if you don't consider frequency, you will underestimate the size of the black hole. Here is a more detailed comparison of one scenario. So if you run the only power flow without frequency, it only just take one stage to finish. It seems to be just single contingency. But if you run this frequency-dependent power flow model, it will tell you there are 3 stages. The one failure will cause maybe a frequency event, like frequency drop to a certain level, you need to do some load shedding, and they can propagate more stages. Here's another comparison, comparing the frequency independent model and frequency dependent model. They can give you very different result. So this one tell you, if you only run power flow to simulate cascading failure, that's not accurate because power flow, any power flow solver will assume 60 Hertz, right, from the first event until the end of the simulation. But under cascading failure, the frequency can change largely. So you need to integrate the frequency division into your simulation, even you don't want to run time domain simulation. So next slide give you some a couple of ideas to integrate transient stability assessment. The first idea is you can add dynamic simulator into the OPA model. Okay, when after any line trip, you will call this dynamic simulator to check the violation of dynamics, like either voltage or protection, and then you continue running the steady-state model. So that can improve the accuracy. So you don't have to run fully dynamic simulation. You only just run maybe 10 to 20 seconds right after any line switch. Once the system is stabilized or almost entering the static condition, you can just stop the dynamic simulation. Another idea is you can utilize the energy function to even speed up this dynamic process. You can use any function to predict any stability issue without running time domain simulation. But in order to estimate any function, you definitely need to estimate the boundary of the system domain of traction. So that can be a challenging question, but you can use the trajectory of your simulation, try to predict. So there may be some different options. So here, it just compare the OPA model with any function only, and to the full dynamic simulation and based on the accuracy. So key factor here is just based on the step, how you search the boundary. So the more step you take, it will be you will more accurately get the boundary for transient stability, but will take a longer time. So if you only take 2 steps, so the accuracy for stable and unstable cases will be higher than, for stable will be higher than 99%, for unstable will be 95%. So if you take more steps to search for the boundary, it can be both higher than 99%. So if you compare different models for the time cost, so one is the OPA model embedding the transient stability simulation. The second, the OPA model embedding any function. So with transient stability simulation, it will take like 12 hours to simulate the cascading failures for the whole data set. But only using any function, it can be largely speed up the simulation. Then you can compare a different OPA model. The first OPA model is just an original model without a transient stability scenario. So it will, the model tells, so the average number of line outage will be 6 to 7, and average load loss will be like more than 300 megawatt. But if you consider transient stability, using the time domain simulation and any function, they gave a very similar result, but you see they are much more severe than OPA only model, which means you do need to consider transient stability to make your simulation more accurate. So either using the time domain simulation or any function. So this slide just tell you, you actually can integrate more information to help you simulate the cascading failure more accurately. For example, you can collect the weather information about the ambient temperature in real time, or the wind speed in real time, or even the tree density to help you to locate which area you have more chances to have the short circuit fault. Using the data, you can simulate. For instance, you can use this attribute standard to simulate the line temperature evolution based on the temperature and the wind speed. And this tells you how the temperature will go up, and that can increase the cycle of transmission line. Then compare the cycle of transmission line and also the tree density, you can determine the high risk region where the cascading failure can initiate. Okay, so you can choose N-1 contingency from that area. So there's more details from those two publications. The next type of model will be data-driven model. So study the interactions of failures. So for these models, we need to cluster the failures in each cascade by generations, and we can assume like a causal relationship from one failure to another, such as we can rank the causalities or the importance of those failures. And then we only visualize the most important failures, most important linkage of failures. Then we can do some prediction. So this figure shows we can cluster, so each column indicate one cascading failure scenario from the initial contingency until the end of failure. So we have many different cascading events. So we can organize those events by generation. So in each generation, we can treat failures as concurrent failures. They don't have causal relationship. But from a generation 0 to generation 1, there could be a simple causal relationship we can utilize. So our goal is to generate such a figure. They can tell the correlation between failures, and we can highlight the most important failure and linkage, and we focus our mitigation strategy on those most important component and failure. This just gave you an idea of some assumptions. If you have one failure cause multiple failures, and based on the likelihood, you can simplify the connection. Just give you a simple or more critical figure. And this just gave you an idea. So based on your data set, you can maybe one failure cause second cause third, but third can also cause the first. You can break that linkage to make such figure be a cyclic, such as you can have more accurate estimation about the likelihood of the failures. You can also organize those critical component and the linkage of failures by layers. So each layer can select a specific focus. For instance, so here we can select line outages, load shedding, electric distance. So for line outages, I only just identify the failures which can cause more line outages of other neighbors, other areas. But for load shedding, I will identify, I will rank failures which can cause more loss of load. And electric distance will identify the failures can cause bigger, the propagation over a larger area. So we can choose different indices and to identify the critical linkage. So here I gave you one idea. If we show the detailed interconnection between failures for the second layer, which is about load shedding. So this one visualizes top 100 links and top 20 components. So if you visualize all potential components and linkage, that can generate a huge graph. But this one just tell you the most important component and linkage you want to analyze or mitigate to prevent to mitigate the loss of load. Here it just shows such idea can be scaled up for Eastern connection study to show the interaction between failures. Okay, how are we going to design the mitigation strategies using this interaction graph from its multiple layers? So we can categorize the mitigate outage using these figures. So we can, because each layer may have different index, like the first layer could be about line outage, second layer load shedding, and last layer can be propagation distance. So if you're only able to mitigate a number of lines with limited time, you can choose your focus. So if line outage is not a really big concern, largest concern to your system, you want to mitigate load shedding, you can focus on the critical component linkage in that second layer, or you can choose other layers. So typically for most of cascading failures, in the early stage, there are not many loads to be shed. So basically, you will see some outages of lines, but the load remain about the same. But in the middle stage, you're going to have more loss of load. And so the focus need to switch to the second layer about load shedding. And in the late stage, the propagation of failure will from local area to wide area. You need to focus on the 3 layer. So if I'm an operator, I have those interaction graph generated offline available. So I can visualize as 3 different layers. So when the cascading failure initiated, I need to focus on the first layer to mitigate the line outage. But if I already moved to the middle stage, I need to focus on the mitigation of the line, the load shedding. And in the third stage, I need to focus on the propagation to mitigate the propagation. So this table just gave you a proof on what I just conclude. So just by checking different strategy with different focus, for instance, you can focus on line outage, load shedding, electric distance, or focus on everything, or focus on maybe 2 of the 3 indices, you can have different results. But if you don't you only just mitigate all the lines, all the linkages randomly. It doesn't give you any positive result. This slide just said you can also add transient stability into this induction graph to indicate which component can cause transient stability. Yeah, you can find that paper. This paper said you can actually develop induction graph for individual region. Okay, and then when cascading failure happens, they can just start from a local region, but then it will move to the remote region. So there will be some component or linkages connecting two components from different regions. So you need to be prepared about such a propagation from one area to another area. So those linkage or component called key interregional component or linkage. Those are really where you want to mitigate cascading failure and from the wide area propagation. This paper did a study on like 3 regions in China. This is in the state grade of China. There are multiple regions. So cascading failure can start from region B, but they don't want it to propagate to region A because that's a very important load center area. So they use the induction graph to monitor how the failure will propagate. So once they involve some interregional component, which means the next step, it will be flying over to the remote region. So it will impact to that region. So that's when you need to do the mitigation action. So they just compare. So if you use this induction graph, consider that interregional component that can largely mitigate the cascading failure for both this local area and also for that remote area. This is very interesting work finished by and also published by my student. That also gave you another idea how to visualize such a graph. So you can use each component as one node of the graph. You can use the status or state of the graph. So if you use this state, you are going to make the induction graph be a Markov chain model. Okay, so you're going to give more accurate probability of the failure propagation. And you can use a matrix to categorize this graph. There's a Markov chain model. And you can even do a model analysis to calculate eigenvalues. So eigenvalue will have multiple types. It will be like a real eigenvalue or even composite eigenvalue. So if you do such study for MCC system, there are many different modes. So each mode will indicate some potential way to propagate for failure. For instance, this like a lambda equals 1 just indicate failure once they enter this state, it will stay there. They don't cause other propagation. So this is like a local mode. There could be some other trivial mode, which means eigenvalue becomes 0, the failure won't propagate. And there could be some other transient mode or complex mode. Complex mode indicate the failure pattern will oscillate, will repeatedly appear on your system after generation by generation. So this slide just visualizes the mode shape of a 2 complex mode on the MCC system. So both modes indicate there's some potential loop. So if you start from a failure in this state, it then cause another state, and after several propagation of steps, they will come back to the same state. So if you don't mitigate the component involved in those failure, this pattern may repeat. So that can cause more wide area failures. So if you compare different strategies, for instance, you use eigenvalue to mitigate the component highly participating in the critical mode, you can design some strategy, or you can just focus on the mitigation on the most frequently failed line. So if you compare those strategies, it tells you if you randomly improve the capacity of the line, it doesn't help much in terms of the reduction of the black holes. But if you only upgrade the lines, which just mostly frequently happen in the past, that can improve, reduce the likelihood of some cascading failures. But if you use this eigenvalue to focus on only the most critical mode of the cascading failure, you can be more effectively to mitigate the large size black hole. Okay. I want to skip this one. This one just indicates if you develop more complex Markov model that can help you to estimate the risk of cascading failure and also design the more accurate mitigation action. The last slide, just some conclusion or some takeaways or my suggestion. First, efficient cascading failure simulation have to consider multi-timescale dynamics. You need to focus your modeling and simulation on only just key mechanism of failures propagation. So if you want to have very fast simulator, the quasi-static model or simulator is recommended, but you need to consider some stability criteria. Okay. The second type is if you have a lot of event data, or you can simulate cascading failure, you can develop the induction graph. Induction graph is a very efficient tool to help you to understand how the cascading failure may propagate on your system. So you can analyze potential mode of propagation, and it can also be visualized for operator to take a proactive action to mitigate failure. So we still need some online decision support system integrating the very efficient simulators such as the OPA-based models or some visualization tools such as induction graph, which is very important for operator to prevent or mitigate cascading failures. Okay, and this is the full list of the papers I utilized today. You can find those papers for more detailed information. So next, I'm going to take questions.
Dr. Sun, there are a couple of questions in the chat feature. Do you are you able to see those?
Trying to find where.
Let me know if you're not able to see them, and I can read them for you, sir.
I don't see anywhere. It could be hidden somewhere.
Hey, you know what?
Let me see. Oh yeah, I got. Okay. All right. Let me. Okay. So the first question is from Blaine Burton. So it's about the one slide, I guess. The curve makes sense conceptually, but it is based on real. Which curve are you talking about?
It was on slide 7, guys. It's up to you if you want to go over it or not.
This one? Which one?
One more.
This one?
Yeah.
Oh, this is just.
I just wondered where you got the data points.
Yeah, no, that's just randomly, just a conceptual figure. I just try to give you an idea. Okay. Yeah, as I mentioned, so for specific system, depending on how strong your system is. So the distribution, as I said, it can be an exponential curve. It can be a power law. It can be a like heavy tail curve. It can be this way or that way or this way, depending on your system status. Does that answer your question?
Yeah, thank you.
The next question is from Lin. Is there a plan to investigate the interdependency between the power system and other system in cascading failure study? If you're asking about my plan, that really depends. That depends on the support. If I get a grant, I can our timing are definitely ready to integrate. So actually, I didn't mention the presentation, but maybe 10 years ago, we did a very preliminary study to consider like a natural gas system and the power system, because the interaction model is okay. It's a data-driven model. It doesn't depend on how you generate the data. It can be from a real event, right? So when you generate such a figure, you can also add another layer. That layer can be communication layer, or you can add another layer like a natural gas pipeline layer. If you have such data, okay, you definitely can use this one to generate such interaction graph. That can give you a bigger picture, right? Maybe some cascading failures start from a pipeline system or from communication system, like 2003 blackout. It does involve some computer programming issues. You definitely you add more layers. that can give you a bigger picture, not just about power system itself. Like the example of like a 2021 Texas outage, right? That's somehow weather related. That's true, definitely very true. You can add more layers. So this technique is purely, this injection graph is a data-driven model. It can be applied to any type of data.
Okay, yeah, thank you, Dr. Sun. Yeah.
The following question, okay. Any other question? Yeah, there's so many papers covered by today. So I try to cover about 19 papers. Yeah, that's a very dense material in this presentation. So I highly recommend, if you're really interested in this topic, just find those papers. Okay.
Well, Dr. Sun, thank you so much. We really appreciate your willingness to talk to everyone today. Guys, this was the final current monthly presentation of 2024. We don't have one in January because it's so close to the first of the new year. But please keep an eye out for an invitation to Dr. Fran Lee, who will be presenting on February the 6th of 2025. So again, Dr. Sun, is there anything else you'd like to leave us with before we finish today?
No, not last one, this one. Just go to buy the 2 books.
Thank you so much, sir. Have a great afternoon, everyone.
Thank you.
Thank you.